1, 2.
All right, so our next talk is Expander Graphs, both local and global, by Michael Chapman, Nati, Linial, and Yuval Peled. And Michael will give the talk.
Thank you very much. Okay, so I just wanted to dedicate this talk to Ella Lipzer. She's a friend of mine, and she passed away 3 days ago. So this talk is dedicated to her. We miss you, Ella. Okay, so a bit about expander graphs. So our setting is that we have a graph G, and it's deregular. So it has some adjacency matrix, and we call such a graph an epsilon spectral expander if its normalized spectral gap is larger or equal to epsilon. The lambda 2 is the second eigenvalue of the matrix. D is the largest eigenvalue of the matrix, so this is the normalized spectral gap. So a known thing about expanders is that they are both abundant and useful. In what sense they are abundant? A random deregular graph is an expander. So in this sense, they are abundant. And useful, I don't have the time to actually motivate why they are useful, but I believe most of the audience know why expander graphs, what expander graphs are good for. Recent results in PCP theory, mainly of Tali and Irit, requires a bit more. And Tali talked about it a bit in her tutorial about high-dimensional expanders. They require a more local view of these, not of regular expander graphs, but they require some graphs that have local expansion. What is local expansion? So taking a vertex V inside your graph, you can define its neighborhood, just all the neighbors on V, and look at the induced graph on the neighbors of this vertex. And you get some new graph. So for each vertex, you get this graph. Usually, we call it the link of this vertex. And for a graph to be called a local expander, we want all these local things, all these neighborhoods, to be expanders themselves. Now, if I claim now that these are rare graphs, in what sense these are rare graphs? If you take a deregular graph, a random deregular graph, most of its neighborhoods will be disconnected. And here you want the neighborhoods to be very well connected, to be very good expanders. So in this sense, they are rare, and actually in more senses they are rare. We have very few examples of such constructions. Now I want to define a new definition. So this is not straightforward related to the previous thing. This is more of a regularity definition. So I say that a graph is AB regular, okay, where A and B are two non-negative integers, if the global graph G is A regular, and every such neighborhood, all the GVs, are B regular. So there are many examples in nature. So the first example is cliques, right? A full graph is n minus 1. If it has n vertices, it's n minus 1, n minus 2 regular. Okay, if you have a graph with with an even number of vertices, you can take a clique and remove a perfect matching and get an n minus 1, n minus 3 regular graph, right? So this is another example, and so on. So there are some very natural examples. The two-dimensional Ramanujan complexes of LVS, of Lubotsky, Vishne, and Samuels are also AB regular graphs. Triangulations of surfaces. So if you have a surface and you triangulate it, the neighborhood of each vertex is a circuit, right? So around each vertex, you just have a circuit. So the neighborhoods will be two regular. So if you take the original triangulation to be A regular, you get some A, 2 regular graph, and so on. So Conlon's hypergraph expanders are AB regular, and Kaufman and Oppenheim's new construction of high-dimensional expanders is AB regular for some choices of subgroups, and so on. So this is a definition. Now, in some sense, usually you give open questions at the end, but I think it's more interesting what are the questions you can ask about these kinds of objects than the actual thing that we showed. I will talk about what we showed, but I think there are 6 points that should interest everyone that actually wants to work on this kind of thing. The first is, as I said, finding interesting families of AB regular graphs. So just constructing infinite families of such graphs is an interesting thing, especially if you can do it in a non-obvious way. So you want the links to actually be at least connected. Let's say you don't aim for links that are very good expanders, just aim to connected links. This is already quite hard. Possible relations between A and B. So are there infinitely many families with, that are 5-2 regular, for example? So I just said a 5-2 regular is a triangulation of a surface. Okay? So are there infinitely many such graphs, for example? I have no idea, to tell you the truth. I know that 3-2 regular graphs, there is only one, if it is connected. So just taking tetraeders and taking the union of such. Disjoint union gives you a family, but these are the only examples. For 4-2, it's only the octahedron. And for the 5-2, I even don't know. I know that there are infinitely many interesting 6-2 regular graphs because there are infinitely many interesting triangulations of a torus. And you can create infinitely many tori that are triangulated with every vertex has degree 6. OK, so this is possible. But for other A's and B's, this is an interesting question. What is the trade-off between the local expansion and the global expansion? So all of us know Alon Bopana. We know that there is some bound on the best, the optimal expansion that you can expect a spectral expander to have. But when I tell you that the links, the neighborhoods, needs to be very connected, it automatically implies that you cannot go through the graph, you cannot mix in the graph as rapidly as you would expect from a regular Ramanujan graph, for example. Right? You need to stay inside the neighborhood, and you can't run away as fast as you would have been in a Ramanujan graph, for example. So there is some very straightforward trade-off between local expansion and global expansion, and we give some results about this as well. OK, another question is what I said, and being an AB expander, having all the links, good expanders, and the global graph and expander, is some high-dimensional expansion, a two-dimensional expansion property. What is the connection to other high-dimensional expansion property, like coboundary expansion, topological expansion, and so on? These are buzzwords, but if you know them, this is a natural question. I think one of the most interesting natural questions is, OK, the regular notion of D-regular graphs, of random D-regular graphs, like the regular models don't generate AB regular graphs. Is there any model that generates them in an interesting way? So you can say that our construction that I will talk about in a moment gives you some model, but it's not an interesting model because it gives only graphs that are like our construction. So is there any interesting model that generates AB regular graphs in some non-trivial way? This will be an amazing thing. And the last thing is taking 1 or 2 or 3 dimensions higher. So as I said, if you take the link, the neighborhood, the one sphere around the vertex, you get an induced graph. What does it mean to be an ABC regular graph? It means that you are globally A regular, like every vertex is connected to A many vertices, and the induced graph on the links is BC regular. So it's just the inductive definition of such things. So finding such graphs, even very simple examples, is quite hard. We don't have any infinite family of such graphs that we know of. Ehud Friedgut recently found an ABCD an infinite family of ABCD regular graphs for which the links are connected for some of the dimensions, which was very interesting, but still this is a wide open, quite wide open question, but building higher dimensional, higher dimensions than this. Okay, so I'll talk about our results. So the main thing we've done is giving a method, defining some kind of product, of graph product, that creates an AB regular graph out of just a D regular graph with a large enough girth. Okay? This gives only connections between A and B that are about square root. Like with our constructions, B is about the square root of A. So for the answer, for the question of what are the possible relations between A and B, this construction gives only these kinds of connections, about square root. For our construction, give connections to show connections when do you have discrepancy, co-boundary expansion, geometric overlap, and mixing of the up-down random walk, which if you heard of many recent results are related to this up-down random walk. You move from an edge to an edge through a triangle and so on. So mixing of these kinds of walks are very interesting in recent time. And the last result I just want to say is that we give some kind of an Alon-Bopana. So as I said, if you are an AB regular graph, you cannot expect, even if the links are not connected, just being AB regular, just the fact that you have some triangles, a lot of triangles in your graph, automatically implies that you cannot be Ramanujan in the usual sense. And we give another bound, which is the correct Ramanujan for the AB regular graph. And we show that if the links are connected, you cannot even achieve that. That if the links are very good connected, you cannot even achieve the correct Ramanujaness for AB regular graphs. Okay, so after all these talks in the air, I'll explain our construction. So given a multiset of non-negative integers, so you just give me a set of integers with some, you can give me the integers with some repetition, and given a graph with a girth that is larger than 3 times the largest number in this set of integers. Okay, so I have this kind of graph and this kind of set. And I want to define you the polygraph defined by these 2 inputs. So the vertex set of the polygraph is just tuples that are of the size of the number of integers in the set. So if there were m integers in the set, the vertices of our new graph is just m tuples of vertices of the original graph. And 2 vertices are connected if and only if now in every graph there is the notion of graph metric, of the shortest path between every 2 vertices. So I can just check what is the shortest path between V1 and W1. What is the shortest path between V2 and W2, and so on. And I will get some set of integers, some multiset of integers. If this multiset is the same as my original multiset S, I define these 2 vertices to be connected. So let's see a very crude illustration. This is maybe the worst illustration anyone ever done, but this gives some idea of what I mean. Okay, so you have m copies of the graph. You choose V1 from the first copy, V2 from the second copy, and so on. You get 1 vertex. So every vertex is just a tuple of these vertices. And you take another tuple, W1, W2, W3, and so on. You measure the shortest path between in each copy between V1, W1, and so on. You get some multiset, and if this multiset is S, you define them to be connected. Okay, so it's nice because you can interpret this with known graph products. So if you look at the adjacency matrix of the graph I just told you about, it's a sum of Kronecker tensor products of powers of the original adjacency matrix. Okay? So the tensoring is over the numbers between 1 and m. And you see there's a sigma there. So the sigma, the sum, runs over all the sigmas that are the arrangements of the set S. So for example, the set 1, 1, 0, okay, it can be rearranged as 1, 1, 0, 1, 0, 1, and 0, 1, 1. So the adjacency matrix in this case will be the tensor product of the adjacency matrix twice and then the identity once in the middle, and the identity once in the left side. So in this sense, you get all the possible arrangements of S. Now, this is very good because whenever you have such a nice equation that defines your adjacency matrix, you can automatically conclude some spectral facts about your new graph. Right? You will automatically know what are the eigenvalues of your new graph. And they are tensoring of eigenvalues and sums of eigenvalues from the original matrix. OK, so this is very nice. Now I just wanted to give a small thing for you to feel that check that you can create the tensor power of a graph using this definition, and also the Cartesian product of graphs, the Cartesian power. So both notions of products of powers in this scenario can be achieved using this definition. They are just private cases of this thing. OK, so the fact that polygraphs are AB regular is easy to show. The problem is that maybe they have no triangles. So the Cartesian product of two graphs clearly has no triangles, right? It's bipartite, right? So not always this construction gives you interesting AB regular graphs. And actually, we gave some conditions in which, at least in the case that S is of size 2 and 3, we can tell you when B is positive. But in general, we don't even know whether it's algorithmic, it's easy to compute. Like, given an S of size 100, tell me whether the B with respect to this S will be larger than 0. This is an interesting question, and we couldn't give it a complete answer. So if one of you would know, this will be very interesting. So as I said before, the polygraph just inherits the global spectral expansion of the original graph. So in this sense, this is quite easy. But I wanted to say something about the local expansion. When we originally published, thank you. When we originally published this paper, we only showed that the local graphs are connected, like the links are connected. But then people told us, why? But this is not what you want. You don't want the links only to be connected. You want them to be good expanders, okay? Or at least give us some numerics about how good of an expander the links in your graphs are. And we worked a bit more, and we got this kind of result. So if you have S to be just 3 numbers that are all even, so for example, 2, 0, and 2 is an example of such a graph, such an S, or 2, 4, 6, and so on. Then we can show some local expansion, like we can give a local expansion for a bound on the local expansion of our graphs. But I must say that it's far away from what we believe is true. So this is, again, we can show that there is some local expansion. But we believe that and you can see that the global expansion depends on the regularity of the original graph. Our bound depends on the regularity of the original graph. But actually, we don't believe that this is true. Like, we conjecture that the local spectral gap of all our graphs, or of all our constructions, should not depend on D. Okay? And if someone would have something interesting to say about that, this would be amazing, because our methods cannot do that. OK, so I'll just move along. I'll just say that, Yeah, that we saw that for different S, you get different things. So you don't have co-boundary expansion for the 110. You don't even have discrepancy. So even the mixing, like you can find two very large sets that are disconnected in this graph. Okay. You can say some things about geometric overlap and rapid mixing and so on, but yeah, I need to finish. So I'll finish and just say that thank you for listening.
All right, maybe we can have our next speaker start to set up while we take a question or two. Yes? Oh, you're the next, okay, yeah. All right. All right, thank you.